Hello, everyone. This is a new IITT session or lecture or talk. It's interactive, and this time it's about engineering practice, risk assessment and management, a very important topic in geotechnical engineering, actually in all of engineering, following a major survey done by the International Society, Are We Over Designing? And today I'm going to introduce super nice, important experts from around the world. I will share my screen. Um, Today, I think this is the IITT number 28. It's gaining momentum, these talks, and importance. And really, today's talk is very important. Just this morning, we were debating with a client over in designing a new port with the difference between two solutions, between 28-meter deep piles and 55-meter deep piles. Look at the difference. And I think with today's talk, we will have the answer. Professor Michael Hicks from Delft University, the chair of TC304, welcome. You are the expert and showing us the benefit of probabilistic design framework. Professor Zi-Jun from China, University Chengdu in China. He's a corresponding member of TC304 and a member of TC309. Monte Carlo simulation for full probabilistic general design is his expertise. I remember Monte Carlo simulation. I barely understood it when I was doing grad school. Professor Suzanne Lacasse, I'm not going to introduce you. You are one of the top engineers in geotech worldwide. I just gave you the most prestigious award in Norway last year, the ILAM Lifetime Achievement Medal. You're the expert with NGI, GTC core member, GTC1 Joint Technical Committee, combining all geoengineers worldwide. Earlier TOC chair of ISSMGE, I cannot stop it. So we are very happy that you are with us, and we're keeping you till the end because you are la creme de la creme. Risk-informed decision-making examples from practice is what you're going to show us today. I can't wait to hear all of you. I'd like to give the stage now to Michael, Professor Michael Hicks. The stage is yours if you like to share your screen.
Okay, can everybody see that hopefully?
Yes, I will put myself in mute for the background noise if you like to do so, all of us.
Okay.
And if we interrupt, feel free. It's interactive when we see the need for extra clarifications.
Okay. Thank you very much, Mark. So so this is the International Interactive Technical Talk by TC304. So we are the Technical Committee for Engineering Practice of Risk Assessment and Management. And the sort of title of the theme that myself and my colleagues are going to talk about today comes under the sort of umbrella of the benefit of a probabilistic design framework. So this is the outline of my own presentation. I'm going to start off by giving an overview, first of all, of TC304 and its activities. And then I'll introduce the theme of this technical talk, the benefit of a probabilistic design framework. I'm going to talk a little bit about uncertainty in geotechnical engineering. And I'm going to give the example of soil spatial variability as one particular source of uncertainty in geotechnics. Then I'll talk a bit about how we can take uncertainty at the material level and see how it propagates uncertainty to the structure level. And for that, I'm going to illustrate a very, very simple Monte Carlo simulation of slope stability. And then I'll talk a little bit about reliability versus factor safety mention very briefly the idea of reliability-based characteristic values before some concluding comments. So TC304 has 99 members from around 30 countries. We have normally 2 technical meetings per year, either online or in person, or maybe as hybrid. So this is the hybrid meeting we had in Oslo at ISGSR about a month ago. In the technical committee, we have working groups, and these working groups work on, for example, recommendations and guidance. So one particular working group we've got at the moment is looking at the recommendations and guidance on the homogenization of ground properties. So we produce state-of-the-art reviews. So I've given a couple of examples here of previous state-of-the-art reviews that we've produced. We've also compiled a very extensive publicly available database, for example, on CPT data, for example, multivariate soil block property data, geospatial data, as well as reference lists. So overall, the technical committee does a lot of work in dissemination. We also organize online forums. So these typically last about half a day. They're a bit like a mini symposium at a conference. And for example, we ran one on quantitative risk assessment of geohazards in November last year. We had about 50 people attending online. And we have one tentatively planned for December this year on Bayesian methods. We also run a lot of short courses for industry and academia. So at the European conference in Lisbon last year, we ran a course, Why is a reliability-based design framework beneficial for industry? And then we followed this up at ISGSR with a course called Reliability-Based Geotechnical Design. We have one honor lecture, that is the Suzanne Lacasse lecture, for which we've had 8 lecturers to date. And we run a lot of student contests. Often it's in collaboration with other TCs, in particular with TC309. We run a number of student contests, for example, on machine learning. We do a lot of work supporting conferences, scientific committee roles, organizing sessions at conferences, judging competitions, running short courses, as I've already mentioned. One particular symposium that we support is the International Symposium for Geotechnical Safety and Risk. But we also organize our own conferences. So we have one planned, an international workshop on risk and uncertainty for June next year in Shanghai. So moving on then to the theme that we want to present today, the benefit of a probabilistic design framework. This photograph
I'd like to congratulate you first for being such active TC.
Okay.
You are a leader in.
Thank you. Thank you.
You're a role model for, I hope all the TCs are like you. Excellent. We're so happy. I mean, you are the real horse that keeps ISSMGE going. Thank you so much. I'll try to be in Shanghai with you.
Okay.
That's a promise. Especially that it took so long to have the visa, so I have to use it.
Okay.
Go ahead.
Okay, so yeah, to the theme of that we are presenting as the 3 of us, the benefit of a probabilistic design framework. This photograph is taken from an area called Leendert de Boerspolder in the Netherlands, and what you can see here in this picture are the crests of regional dikes, which are basically protecting low-lying land behind the dike crests from water. So these dikes you can see here on the land side, they're typically about 1.5 meters high. This picture shows you how global safety factors for regional dikes in the Netherlands have evolved over the years. So the vertical axis is required global factor of safety, going from 0.5 on the vertical axis up to 2. And the horizontal axis goes from 1973 on the left all the way through to 2009 on the right. And in this picture, the red zones indicate unacceptable factors of safety. The green zones are acceptable factors of safety. And then the orange and yellow zones may or may not be acceptable depending upon the situation we find ourselves in. And so what you can see from this particular illustration is that there is uncertainty about what the global factor of safety should actually be. And what I could say is that the significant stretches of the Dutch flood defense network do not meet current safety guidelines. However, this includes, for example, 400-year-old dike sections that have never failed. So something isn't quite right somewhere. Following a similar theme in the Netherlands, there's also significant stretches of the Dutch railway embankments that do not meet current safety guidelines. And in the future, railway embankments will be subjected to an increase in loads and an increase in the frequency of loading. So there is a need to take account of uncertainties explicitly in slope stability assessments. Now in this presentation, I'm going to focus on the uncertainty which is due to the spatial variability of soils. And as we know, spatial variability occurs at multiple scales, from the very, very small scale, such as shown in the left-hand picture here, of peat under the microscope, right the way up to the very large scale or regional scale, as you can see from this aerial photo of a delta on the right-hand side. But what I'm going to focus on in this presentation is one particular scale. I'm going to focus on spatial variability within a single soil layer, within a so-called uniform layer. So here we have the spatial variability of a material property X through a so-called uniform soil layer. And what we can see is that, in fact, the layer is anything but uniform. But what we would do in a standard or deterministic analysis is we would make use of a single value for the layer in any design. For example, we might take the mean value mu, or we might take the lower bound, or we might take the upper bound, or some other representative or characteristic value for the layer. And as a result, we would end up with a single factor of safety for our structure. In contrast, what we would do in a probabilistic or stochastic analysis is we would make use of all the data from the layer, and we would express it in the form of a probability density function characterized by the mean mu and the standard deviation sigma, and also by a third statistical parameter theta, which is illustrated in the left-hand part of the picture, which is called the scalar fluctuation. It is a measure of the correlation of properties of similar values. It's a measure of the distance between properties, or a measure of the distance between regions with similar material properties, I should say. Perhaps a better illustration of the scalar fluctuation is to show this picture here. So this is a picture of spatial variability in 2 dimensions. And what we're looking at here is the spatial variability of state parameter of a uniform sand layer. State parameter, of course, is something which is similar to relative density. And this uniform sand layer comes from the extension at the port of Rotterdam in the Netherlands. And what you see in this picture here are the locations of 4 CPTs. And what you can see is that this uniform sand layer, again, is anything but uniform. The red zones are areas of sand which are in a particular loose state. The blue zones are for material that is in quite a dense state. The spatial variability at the locations of the CPTs is known from the CPT data. But of course, what we're not so sure about is what the spatial variability is between the CPTs. And so we have to make use of numerical modeling to predict the spatial variability between the CPT locations. And so that leads to some degree of uncertainty. So the thing I want to highlight from this picture is that the uncertainty that arises due to spatial variability is due to incomplete knowledge about the site. In this case, we've only got 4 CPTs, and we're uncertain about the spatial variability between the CPTs, and we need to take account of this using probabilistic methods. Now, of course, because we're uncertain about the spatial uncertain about the material profile everywhere at the site, this leads to uncertainty when it comes to analyzing the performance of a particular structure. There is propagation of uncertainty from the material level to the structure level. And so what I'm going to do now is give you a very, very simple illustration of the propagation of uncertainty from the material level to the structure level by looking at an idealized slope. It's a 1 in 2 slope. We're analyzing it by finite elements, and this slope is characterized by a spatially varying undrained shear strength, as you can see shown by the example in the bottom of the picture. Now, for this particular slope, the mean undrained shear strength increases linearly with depth, but superimposed on top of that is a spatial variability characterized by a standard deviation of undrained shear strength and by a scalar fluctuation or correlation distance in the horizontal direction and a different scalar fluctuation or correlation distance in the vertical direction. And what you can see in this picture here is one numerical prediction of the spatial variability for this slope based upon the underlying mean, standard deviation, and the scales of fluctuation in the two directions. And in this picture, light areas are low values of undrained shear strength, and the dark areas are higher areas of undrained shear strength. To begin with, what I'm going to show you is what happens if we try and calculate the factor of safety of this slope, ignoring the spatial variability. In other words, only taking account of the underlying mean undrained shear strength. And the way we work out or compute the factor of safety
Michael,
is, sorry, yes, Mark.
sorry to interrupt. Are you changing slides or we're still on the same slide?
We're still on the same slide. We have a picture of a slope here, a mesh at the top, and we have
coloring.
Spatial variability below it, yes.
I felt that you might have changed the slide. Okay,
No,
keep going. Sorry to interrupt.
Just about
This
to change.
difference, the previous slide with the color spreading between the CPTs were generated by numerical modeling or some sort of GPR or some. Okay.
That's right. So in this picture here, the spatial variability is generated by what we call a random field generator, and the random field generator is based upon the mean, is based upon the statistics of state parameter that have been derived from the site. But this numerical prediction is constrained at the actual CPT location. So although it's a numerical prediction, it matches the data at the CPT locations. But the numerical prediction is generated based upon the statistics of the state parameters, so the mean, the standard deviation, and the scales of fluctuation. That's correct. So in this picture here, yes, the picture at the bottom is another random field. This is this time of undrained shear strength, and this is generated based upon the statistics of the undrained shear strength, the mean, the standard deviation, and the scales of fluctuation. Now, if we just first of all analyze this problem using the finite elements and the strength reduction method, we get a graph something like this. So the vertical axis is crest settlement non-dimensionalized with respect to the slope height, and the horizontal axis is a scaling factor. And in the strength reduction method, what we do is we gradually scale down the strength of the material until the slope falls down. And the amount by which we have to scale down the original strength profile by gives us the factor of safety of the slope. So in this particular example, if we just analyze the slope taking into account the mean properties of the slope, the factor of safety that we calculate is 1.6 in this case. And because it's a very simple problem, it agrees with an analytical solution. If, however, we carry out the same analysis, but now we take account of the spatial variability superimposed on top of the underlying mean trend for the undrained shear strength, what we find is we will get a different response. In this case, the factor of safety that we compute is only 1.45. However, what you've got to remember is that when we carry out an analysis like this, we are making numerical predictions of the spatial variability for the slope. And for a given set of statistics, for a given mean, a given standard deviation, and a given scale of fluctuation, we could come up with lots of different predictions of what the spatial variability will look like for the slope. And they will all look similar because they've all been generated using exactly the same set of statistics, but they will all be slightly different with respect to where the strong and the weak zones are. And each one, when they're used in our slope stability analysis, will give us a different response of the structure. And so if we go back to this analysis and we generate another prediction for the spatial variability for the slope, and we analyze the problem again, then we may find that the factor of safety is actually bigger than 1.6. And if we generate lots of predictions for what the spatial variability is like of this slope based upon the same input statistics, we get lots of possible solutions. And in here, what we're doing is we are carrying out what we call a Monte Carlo analysis. So we carry out a Monte Carlo analysis to look at the full range of possibilities for the slope response. And then what we do is we can plot the predictions for the factor of safety as a probability density function. And we can approximate that probability density function by an analytical distribution, as you can see in this picture. I think in this picture here, we carried out about 500 realizations for this particular problem. Now, what you can see in this picture are two main things. The first is there's a wide range of possible responses of the structure due to the fact that we're uncertain about the material conditions in the first place. The second thing is that the mean probabilistic response is a lot weaker than the deterministic solution based only on the mean strength profile. And the reason for this is because failure is attracted to weaker zones and it tries to avoid, where possible, the stronger zones. Now, another thing we can show on here is we can show the probability of failure. The probability of failure is the area underneath the probability density function for values of factor of safety less than 1. And of course, the reliability is the area underneath the probability distribution for factors of safety greater than 1. Now, the reason we have this wide range of solutions is because we are uncertain about the material profile at the site. We may be confident about the statistics of the shear strength at the site, the mean, the standard deviation, and the scale of fluctuation, but we don't know exactly where the weak and the strong zones actually are. However, if we constrain the predictions of spatial variability by on-site data, for example, at the location of CPTs, or if we carry out additional CPTs, this reduces our uncertainty in the spatial variability at the site. And so what it means is that when we carry out this analysis, the probability density function of factor of safety will get narrower. When it gets narrower, what will happen is probably that the probability of failure will reduce. If that's not definite, it could actually increase, but it's quite likely to reduce, so giving us a more efficient solution because we have taken advantage of additional available site knowledge. So that's the end of my very simple introduction to this topic. So I have a few concluding comments here before I finish. The first is that a conventional factor of safety tells us nothing about the probability of failure. A probabilistic approach provides a more rational framework for assessments of structure response. It can lead to more efficient safe designs and a reduction in over-conservatism. It is possible to derive reliability-based characteristic values and partial factors. And these can be then used in what we call a semi-probabilistic approach. So what we can do is we can use these reliability-based characteristic values and partial factors in a standard deterministic analysis to try and achieve a target reliability level. However, if we use if we do a full probabilistic analysis instead, such as a Monte Carlo analysis I've just illustrated, that actually negates the need for characteristic values and partial factors, because if we carry out a full probabilistic analysis, that analysis itself achieves the target reliability level directly. Okay, thank you. That's the end of my presentation.
Very good.
I'll stop sharing.
Great intro. Thank you for introducing the importance of reliability analysis.
Okay.
Professor Chow, the stage is yours.
Yes, thank you. I'm sharing my screen. Can you see it?
Not yet. Yes.
Well,
Great. Monte Carlo simulation. You're complimenting Michael.
yes, actually, thanks, Professor Hicks, for the introduction. It makes my talk easier to understand. To understand, I think. Hello, everyone. Who may watch this video in future. I'm Zi-Jun from Southwest Jiaotong University, China. It's my great honor to give this talk online. Following the instruction by Professor Hicks, I'm going to demonstrate the benefit of probabilistic design framework by application of Monte Carlo simulations. The presentation will highlight that reliability calculation is not the only value of Monte Carlo simulation. Here is the content of this talk. I will start with the discussion of the relationship among the four concepts very quickly. We have to admit that nothing can be said to be certain, except the world is uncertain. Uncertainties are everywhere, including arbitrary uncertainty that are inherent and reducible and irreducible, as well as epistemic uncertainty that depends on the state of knowledge. I think Professor Hicks has demonstrated that if we have more science information, the uncertainty can be reduced. Rational quantification of the various uncertainty is crucial to reliability assessment and management, as most commonly used tools for uncertainty quantification. Probability is a mathematical model. It provides a suite of models for quantifying various uncertainties. With probabilistic modeling of uncertainties, reliability and risk can then be calculated to support engineering decision-making, like site investigation, design, and maintenance, etc. From the above, we can see that uncertainties are involved in collected information. Probability quantifies uncertainty mathematically, allow propagating them into decision-making in engineering context, while calculated reliability and risk. We have to note that the calculated reliability and risk are actually nominal values. They depend on the available information and mathematical models of uncertainties, as well as deterministic analysis models. For example, the model used to calculate the safety factor. As for geotechnical design, uncertainties in geotechnical properties, underground stratigraphy, and calculation models and loads are relevant. Due to these uncertainties, the deterministic analysis given nominal values of input parameters cannot explicitly account for the uncertainty in calculated design performance measures like safety factor. In contrast, probabilistic analysis allows quantitative propagation of uncertainties in geotechnical design practice. The design procedure that aims at finding feasible designs satisfying the prescribed reliability level of structure is referred to reliability-based design. They can be implemented either in a semi-probabilistic format, such as load and resistance factor design and the partial factor designs, or full probabilistic design format. As stated in the Annex of D of ISO 2394, the key goal of geotechnical RBD is to achieve a more uniform level of reliability than that implied in existing allowable stress design. This is very challenging, at least partially because the calculated reliability is a nominal value. It depends on uncertainty representation, modeling, as well as the performance modeling, which are hard to standardize for the design procedure due to a number of distinctive elements of geotechnical RBD, such as the spatial variability, unknown failure modes of slope, selected design values that were mentioned by Professor Hicks. These elements, however, can be taken into account with relatively ease under full probabilistic design framework in comparison with semi-probabilistic framework. For full probabilistic design requires explicit reliability calculations of the different designs. It provides significant flexibility in uncertainty modeling and performance modeling, hence particularly suitable to geotechnical designs. However, uncertainty modeling and reliability analysis requires expertise in statistics and probability theory, which may not be available to geotechnical practitioners. This necessitates a practical and conceptual simple design framework that allows extending conventional deterministic design calculations to full probabilistic design in a straightforward manner. Monte Carlo simulation provides a conceptually simple and robust method for reliability calculations in general. Basically, it does generates a set of random samples of uncertain parameters, followed by calculating their corresponding design responses. The random samples are essence of Monte Carlo simulation. They represent numerically the PDF, probability density function of uncertain parameters. Based on these random samples, probabilistic reasoning can be reduced to repeatedly calculating the design responses of different samples and a statistical analysis of these calculated design responses, so that probabilistic reasoning can be performed in a non-intrusive and discrete manner. This is one important value of Monte Carlo samples in the sense that it allows straightforward extension of conventional or deterministic design calculations to full probabilistic design. To improve the practicality of Monte Carlo simulation-based reliability-based design, some toolbooks can be developed, such as the Excel 8-in that we developed in our previous study. We call it geotechnical reliability-based design based on simulations. With GeoRBDS, the deterministic model is deliberated, decoupled from uncertainty modeling and propagation. Monte Carlo simulation allows full probabilistic design to be implemented in a non-intrusive manner, so that geotechnical engineers can focus on deterministic modeling where they're familiar with. As an illustration, a semi-gravity retaining design example is given here. The example was used to illustrate reliability-based design through first-order reliability method by Professor Bigelow. Two failure modes were considered in this example. The retaining wall sits on a stiff clay layer, so the bearing capacity is not considered here. The height of the wall is 6 meter. The top wise and heel wise are taken as a design parameter. Each has 5 possible values and leading to a total of 25 designs. There are 3 uncertain parameters, including friction angle, effective friction angle, the interface friction between the soil and the wall, the adhesion between the wall base and the soil. They are assumed to be normally distributed for illustration. This slide shows the reliability calculation results from Monte Carlo simulations by GRBDS. Besides direct Monte Carlo simulation, the toolbox also allows using two advanced Monte Carlo simulation methods, subset simulation and generalized subset simulation, SS and GSS here. Results from these 3 methods are in good agreement. We can see that. With advanced simulation method, the number of samples needed to achieve reasonable accuracy of reliability calculations is much smaller. The computational efficiency is a key to Monte Carlo simulation. Beyond reliability calculations, Monte Carlo samples can also provide more values in reliability updating, reliability sensitivity, and approximate design point identification. Since the calculated reliability is a nominal value, it should update with the information. A typical scenario is that geotechnical site understanding can be improved with a collection of site information. For example, soil parameter distribution can be changed with the different site information. For this scenario, the calculated reliability is changed as well. The updated reliability can be recalculated by repeatedly performing Monte Carlo simulation or other reliability methods with different probability distributions. This may computationally expensive, particularly for direct Monte Carlo simulation. Alternatively, this can be achieved by reweighting samples according to the updated probability distribution. For example, a set of direct Monte Carlo samples have been generated for a given design, and their corresponding design responses have been calculated. As the probability distribution of uncertain parameters is updated, the likelihood of the samples changed, but their design responses remain unchanged. Hence, the failure probability can be updated by reweighting each failure samples according to the updated distribution. Here is the equation. At the probability, then the reliability updating is achieved in a cost-effective manner. This allows link the site information to a reliability-informed design decision making. Why? Oh, sorry. For example, the probability distribution of the 3 parameters in the gravity wall example are updated from the distribution in green line to the distribution showing in the red line. With the generated direct Monte Carlo simulation example samples, the reliability updating with the can be achieved with negligible computational cost. The results are shown to be consistent with those obtained from repeated Monte Carlo simulation runs, for which additional computational costs are required. In design, the sensitivity of failure probability with respect to a model parameter may also of interest. Such sensitivity can be reflected by the failure probability function. That is a function of the failure probability at the variation of the uncertain model parameter, as shown in this figure. After a set of Monte Carlo samples are generated, the failure probability function can be calculated through Bayesian analysis. It's interesting to see that the variation of it's interesting to see that the variation of failure probability with the model parameter depends on how different the conditional distribution and the how difference between the conditional and the unconditional distribution. Such a difference can be simplified, reflected by normalized difference between the conditional and the unconditional mean value of the uncertain parameters. As the conditional distribution is identical to the unconditional distribution, the failure probability does not change with the parameter, which means it's not sensitive to X, vice versa. Hence, post-processing of Monte Carlo samples allows identifying key parameters considering uncertainty. This slide shows the rank of sensitivity of failure probability over different uncertain parameters in the gravity wall example. As for the overturning and sliding failure mode, the most sensitive parameters are respectively the effective angle of friction and the adhesion between the wall base and the soil, which are consistent with the iteration. Post-analysis of Monte Carlo samples provide correct parameter sensitivity information. Besides reliability updating and sensitivity, the design points may also of interest when Monte Carlo simulation method is applied for calibration of semi-probabilistic design codes. Design point is defined as the most probable failure point in literature. By this definition, the design point can be approximately identified from the failure samples generated by Monte Carlo simulation. The accuracy of design point can be improved with the number of failure samples. Despite of this, the approximate design point from failure samples still has the value in facilitating Monte Carlo simulation-based calibration of the RBD codes. The value bridges semi-probabilistic and full probabilistic design. For example, it can be applied for level 3 calibration of partial factor in Eurocode. The red stars here show the design points of uncertain parameters identified from Monte Carlo samples for overturning and sliding failure modes of the gravity retaining wall example. They are comparable with those obtained from the first order reliability method. Finally, I would like to summarize my talk. 4 key values of Monte Carlo samples for geotechnical design are presented here. It can be seen that beyond the reliability calculations, it allows straightforward extension of deterministic design to full probabilistic design. Besides, post-processing of Monte Carlo samples allows efficient reliability updating, identify sensitive parameters, and approximate design points. Last but not the least, Monte Carlo samples may have more values in future with the advances of hyper-performance computing and the increasing of design model sophistication. With this, I would like to end my talk. Thank you for your attention.
Professor, We need a full day with you, not just 15 minutes.
Oh, sorry. I'm sorry.
Excellent, excellent. Nice, nicely put. I hope all the software they provide calculations and analysis instead of giving us one input value to incorporate Monte Carlo simulation based and probabilistic based input values. What do you think?
Sorry, I beg your pardon?
The software available, many softwares available on the
Yes.
market do design for slope stability and finite element analysis. When you input, they provide you one number you have to input. So you have to do all these simulation and probabilistic analysis in your brain as an engineer and give one value to the software. And I
Yeah.
wonder if they started already implementing this, for example, the Monte Carlo simulation
Yes, I think in some
in their
software,
software.
Monte Carlo, yeah. Yeah, in some software, Monte Carlo simulation have been implemented as a built-in functions. And some software are designed to use Monte Carlo simulation, such as I think rock science will provide some software for this purpose.
Very nice.
Yeah.
Well, we're now with Professor Suzanne Lacasse. You're already sharing your screen. We can't wait.
But thank you very much, Mark, and hello, everyone.
It's an honor to have you with us.
Thank you. Hello, everyone from Oslo. And I guess I'm going to give you some example. What do we do with this data that has been generated in the first two lectures? I want to talk about the risk-informed decision making, and with just a very few examples, because in 15 minutes. So a few words about risk-informed decision making, the approach, and then a figure to illustrate the difference between conventional approach and the risk-informed, and two examples from practice, and end up with a few reflection slides. And first, to define risk. Well, here you have an area in Oslo, just south of where I live, and the slope has a high susceptibility to fail. There's a number of houses, but if this slope fails, it goes downwards, and there's nobody living in the area. There's farmland, but there's not even big animals. So you can say that the hazard is high, but the consequences are low. There are no lives at stake. So that is called low risk. Now, world being as it is, developer say, well, we have all this land, maybe we can build some houses and make some money. So stabilization measures were done in the area, where the area shown in gray, to reduce the susceptibility of hazard of landslide. And lo and behold, many more houses were built than what was planned. The problem is the stabilization that was done, it was not known by how much the probability of failure would be reduced. These buildings here, they were installed in 2007, but because there are many more people living on that slope and downward, the consequence is much higher, because there's about 100 buildings there, and there's a lot of people that are at risk. And what happened in 2020 on New Year's Eve at 4 o'clock in the morning, no warning or anything, this slope here failed, and 31 houses were destroyed and 11 lives were lost. And so that the risk is when there's a very large consequence associated with it. If there are no consequences, it's a hazard, but it doesn't mean that the risk is high. So what is risk-informed decision making? It's a structural approach where all insights and requirements related to safety and regulatory issues are taken into account. And you include the mandatory requirements, deterministic analysis, the conventional analysis, risk analysis and risk assessment, and then other aspects like legal, what the law says, costs, and social response. And risk-informed decision-making is a standard way of doing things in Australia, in the United States. NASA uses it. Just to give you a few examples, the government of India and the nuclear industry. The conventional approach, which you all know about, where you first do a design check, factor safety, do a visual inspection, perhaps, compliance review, and the decision is based on standards. Well, with the risk-informed approach, the deterministic is still down here. You gather all information. So all this information is provided by this. Then you assess the hazard, the possibility that a slope will fail or a dam will overtop, and the consequences. And then you create a risk picture. You assess the risk level, and then the owner of a dam or the owner of the slope, he will make a decision based on this available information. So it's informed by risk. And then the risk informed approach also requires that you reassess the risk at regular intervals. And because as population change, as climate change, there are climate change, as new erosion may occur or a new building may be placed in the path of a landslide, this changes with time. I'm just going to mention risk assessment, not so much risk management, but risk assessment, you identify what may happen, identify who may be at harm. You do the analysis. There are several different methods, including Monte Carlo simulation. There is event tree analysis. This is probably the most commonly used. Fault tree analysis, or just simple risk matrix with color code to tell you whether the situation is safe or it should be looked into because the risk is too high. And then the third step is evaluating the results of the risk analysis. A few examples. Here we have it's a port, also south of Oslo, and the entire area is built on fairly soft clay, and in some areas there's quick clay, and it's a very varying profile. Some of it is sand, some of it is clay, and they're not of the same thickness all over. So we're concerned about these 4 areas here. And as you realize from this picture, it's a heavily populated area. All these areas had varying factors of safety, and that's because of the varying thickness of the material. The yellow is the sand. This is just one of the cross section. The blue is clay, and the pink is the quick clay or sensitive clay. And in some areas, those who can read this, you will see a factor of safety of 1. So in many of the areas, I think we did maybe 2,500 stability analysis in the area. The factor of safety was very low and calculated as 1.0. And that just illustrates the weakness of our calculation model, the deterministic one, because it gives you a safety factor of 1, and yet the slope is standing. So if you calculate factor safety of 1, the slope should be failing. So the government decided to build a railway station in that area with high-speed trains. And naturally, this is another area that's appropriated for this. So there are many mitigation measures. The railroad, railroad would be here. And then the port is down south in the bottom here. And there were some fields that were placed to increase the stability in the tow. There were some jet pilings in the area, which weakens for a while, but after the strength gets much bigger. There were some drains that were placed. They've worked, they're still working for the past 4 or 5 years into stabilizing the layer. Again, the station should never have been placed there, but the decision was a government decision without consulting the engineer. So we look at the failure probability and of a large, quickly landslide, and the landslide creating at least one death among the people. We look at many scenarios. I just listed a few here: rainfall for all types of storms, human action, somebody would be filling on top or excavating at the bottom, um, surface water, maybe due to the pipes bursting and then creating erosion. And then even because we have a port here, a ship coming and colliding against the wall. But as the analysis showed, this was a very low probability event compared to the other event, like a natural slope failing. And we use the event tree technique, and I'm not going to explain it to you, but what it does, it looks at the probability of, for example, having a pipe burst and spreading water. And then we add some rain to it, and this is this part. And then we look at the probability of destructive erosion, and can it be discovered in time and repaired? Yes or no? And if it cannot be repaired, will a small slide occur? And will it develop in a very large landslide and create deaths among the people, which is the last step? But I'm showing you just one area. In one area, remember, we have a very large area, so the total probability of failure is much higher than what's shown here. But we divided the analysis in 4 phases. First, it was the natural slope before the start of the work, and that gave us an annual probability of failure of about 10 to the minus 2, which is high, but maybe not so uncertain. It's usual for natural slopes. And then first we had instrumented the area, and then we informed the people that you cannot dig a hole and you cannot put a fill on top of a slope, and making the people more aware, because many of the slopes of the landslides in Norway are caused by human action. And then stage 2 was having a stabilization in part of the area. And then stage 3 was when the stabilization was completed. And right now we're analyzing, we're nearly complete the stabilization. We're analyzing what would be the probability of failure and the probability of a person losing his life or her life in 2030, when the trains will be set in actions. And in this case, you saw that the stabilization was decreasing the annual probability of failure, which was good. But what happened, and it just happened in the last 6 months, so this is the area where we had the weakest slopes. And so we were stabilizing here, putting some piles, and then the displacement downwards were moving further and further towards the port. So we did some finite element analysis and looked at what displacement could be allowed before there would be a landslide occurring. And we had arrived at 12 millimeters, and 17 millimeters was our prediction where the landslide would occur. So with the information, we redid the probabilistic analysis, and we came to a probability of failure, which was about 10%. So within 1 week, we had to evacuate these 3 buildings here, which was very unfortunate. But when we use graphs like this, and like the next one I will show you, the people understood that they were at risk. And although they were very upset in the beginning, they accepted the fact. And now they've all been moved out, and the buildings are being, are nearly, what's it called, deconstructed. There's nothing left right now in this location. The other example is for a dam. And here on the left and the right, I'm comparing one very large rockfill embankment dam. On the left, before it was rehabilitated, on and to the right, after the rehabilitation. And each of these points, it's on a kind of standard diagram showing the annual probability, in this case, of a dam failure. And here the consequence, the number of people of fatalities, number of people who would lose their life. And for each of the failure mode we looked at flood in the winter and the summer. We have in the winter, it's when the glacier melts and the snow melts, and there's a lot of water coming in. We look at internal erosion, we look at an earthquake, and we look also at rock slide falling into the reservoir and causing a large wave. The black point is the sum of all the failure probabilities as the societal risk. The gray area are all the guidelines around the world for where the risk is either tolerable or unacceptable. And the average line here, the dotted, is one that's the most used. So this analysis told us that this dam was not in a satisfactory condition. There was something that was pushing it in the area of unacceptable risk. The rehabilitation was done mainly for this mode of failure by increasing the spillway and preventing it to becoming blocked, because that's what had happened when we were doing the analysis. It was such a bad winter, so much snow. The spillway was completely blocked. And because there was so much snow, it did not melt until June. And so there was much too much water. And the rehabilitation measure decreased the failure probability by this much, and this became much closer to the tolerable zone. The decisions of what to do is by the dam owners, not by us. But this tool is a very good communication tool to people. And this last example, it shows, it compares 3 different dams. The black one is the same that I've shown you before, but I just want to show you the brown point here, which is a concrete dam. It's a buttress dam. And there was some rehabilitation that had been imposed by the authorities in Norway. And the rehabilitation was costing millions and millions of dollars. It did not reduce the risk at all. For this concrete dam, what had been recommended was simply not effective. And again, this information provided us with much better basis to make a decision. In ending, I just want to point out, it's too short to explain everything, is this risk-informed decision-making approach. It adds insight by integrating the risk-based assessment with the conventional safety evaluation and the consideration of a potential behavior under a storm, under a landslide occurring in a reservoir, for example, etc. It provides an improved understanding of safety in the identification of vulnerabilities not considered by standard approaches. You would be surprised when we do this analysis how many experiences we get. Oh, I hadn't thought of that. Oh, yes, that is true. And it's by the people that are the practitioners working at the site. So the risk-informed approach, it recognizes also that engineering judgments and other non-quantifiable factors need to be part of the decision. This is defined in the code. So the decisions are made in a balanced manner and are more robust. So what we need a deterministic analysis, but because of this fixed safety factor, what has Michael showed us, it gives the impression of certainty and no uncertainty. Risk-based analysis, they include the uncertainties and their effect on the safety. They complement the deterministic analysis. And for robust and improved design and decision making, we need both. And in closing, I just want to say something about learning more than just geo. When I graduated, I was completely unidisciplinary, shown on the left. But then we started learning about geotechnical engineering and geology and computer IT, for example. It became multidisciplinary. Then interdisciplinary, but what we need today is this cross-disciplinarity on the right. So we need increased depth, breadth, and integration of knowledge that leads to more sustainable, more innovative, and more complete, more reliable solution. And it certainly represents a new way of looking at geotechnical engineering, and I think that's very promising for the future. This completes my presentation. Thank you very much.
Suzanne, you're always an inspiration. Thank you so much for your slides. Very clear presentation about the risk assessment and decision making. I fully agree with you. Um, I can't tell you how important this talk was to me, and I'm sure for all our viewers. This is recorded and will be published in the coming week or two. I'll let you know. But I like to thank you so much ahead of time before publishing for your time and efforts in preparing. And if you want to say something, you're welcome to our viewers. Uh, Michael, Zi-Jun, Suzanne, thank you so much.